Today, we will be learning how to draw shear and bending moment diagrams using the method of sections. Drawing these diagrams are important because they allow us to visualize the internal shear and bending moment acting along our beam. And this can allow us to identify critical design points, such as the maximum or the minimum shear and bending moment within our beam. In the previous video, we applied the method of section to derive our shear and moment equations along the length of the beam. If you recall, this beam right here is the loading condition we used, and we split it into 3 distinct sections, 1 extra section every time the loading conditions changed, and that gave us 3 equations each for shear and moment, with each equation covering a different span along the beam. The goal for today is to transfer these equations over to our shear and bending moment plot, and this is what we'll find useful. One thing I want to clarify from the previous video is that you'll notice how I left out an equal sign in the domain of the second and third shear equation. So the reason why shear does not have a value at 5, meaning I didn't include 5 in our domain, that is because at x equals 5, which is where this point load is, there's actually a jump in the value of shear, which is also known as a discontinuity. And so in mathematics, if there's a discontinuity, then we simply do not have an exact value of shear at that point. But this is something that we'll be able to visualize even easier once we plot it on our graph. So the first step to drawing our shear and bending moment diagram is you want to go over to your free body diagram of the beam and start by drawing a vertical line under the rightmost point and a vertical line under the leftmost point. Once you've done that, you want to add 2 axes, one for shear and one for moment, and these will be the 2 locations where we plot each of shear and moment. So V represents shear, and we'll want to include our units for each of these. So shear is going to be in kilonewtons in this case, and moment will be in kilonewton meters. And this is because from the very start, we only used kilonewtons and meters when doing our calculations. So once we have our units clarified, we need to declare our positive sign convention. So for shear, we will indicate a positive sign convention using a square with a plus in the middle, and we'll show a clockwise shear, which looks like this. And then for the moment, we draw a smile typically to show a beam that is bending upward. And then we will have 2 moments that are pulling this beam up into a smile with a positive right there to indicate that this is positive sign convention. So before we move on, I want to clarify these a little bit because a lot of people can get confused at this point. But when we have shear and bending acting on a beam, we can actually get 2 different kinds of it. We can either get a positive or a negative, but we need to establish which one are we going to call positive and which one are we going to call negative. So for shear, if I have a beam, I can either apply shear up with my right hand like that, or up with my left hand like that. And so these are 2 different kinds of shear because I'm applying forces perpendicular to this beam. But in one case, the forces, wow, I guess I exceeded the material strength. But when I apply that shear, I will either get forces that are being applied in clockwise or counterclockwise direction. And typically, we will use clockwise as our main sign convention for when we're drawing these diagrams. And for moment, we will either get bending that bend the beam into a smile, or we will bend the beam into a frown. And so typically we use smile as a positive sign convention. And this is important because when we plot our graph, we want to know, okay, at our maximum moment, is this beam bending upward into a smile or downward into a frown? And so these are very important. these are the typical sign conventions you can see, so feel free to get used to these. Okay, and the last thing we have to do before we start plotting our graph is make sure that these equations right here actually agree with the sign convention that we've used for our plot here. So if you remember from the previous video, when we cut a section of our beam, so the section I'm showing you right here is the section we took when we cut our beam in here, and then we guessed that our shear was going to be up, and we guessed that our moment was going to be acting this way. So these equations and their signs are going to agree with what we labeled them as here when we took our section. So for shear, and remember, when we take a section, we're analyzing that point right where we cut our beams. We'll be looking at this point right here. And you'll notice that shear on the right side is going up. But according to our sign convention, on the right, shear should be going downward, which means that this is the opposite of the sign convention that we're using for our plot. So because we based our equations off of that opposite sign convention, we just need to change our signs. So that becomes negative, that becomes positive, negative, negative. And now these agree with the sign convention we use here. And then it's also a good thing to check that our moment agrees with our sign convention as well. So at this point, we have a moment on the right side that's pointing that way. And this agrees with our sign convention here, because we know that at a point on the right side, if the moment is pointing in that direction, it's going to create that smile, and that's positive. So our equations for moment are actually the proper sign convention that we want here. So now, I hope you are all still with me, but if you have any questions, just feel free to comment down below. We now have our proper set of equations that agrees with our sign convention here, and we can begin to plot them. So let's start by labeling the axes as 0 and 0 here, meaning that on this line we'll have 0 shear, and on this moment we have 0 moment. So going from, actually before we go here, each time we have a change in the equation we're using, it's important to label that on our graph. And so we'll see at x equals 4, we have a change, and at x equals 5, we have a change to a different equation. So it's actually a good idea to go to your free body diagram. Okay, go to x equals 4 right here, and just draw a dotted line going all the way down. And then the same thing for x equals 5 right here. And you'll see why that's important, but it helps us divide our graph into different sections where each section has its own equation. And this just makes it a little bit easier to work with. So at the start, we have negative 4x plus 10.33. So what this means is that at x equals 0, we have nothing here. So we'll start at 10.33. And we'll label this as 10.33. And then we go down at a slope of negative 4. So if we go all the way to x equals 4 here, we'll have a negative 16, and that's a negative 16 plus 10.33 is going to be negative. So that tells me that we're going to go into the negative portion of our shear. So then we get to x equals 4 right here. And then we can see that between 4 and 5, our shear is actually at a constant value of negative 5.66. And so we can check what this value is right here, using the equation that we used here. So if we actually just plug in, so we have negative 4x plus 10.33. Let's just see where we ended up on our graph at 4 meters. So we have negative 4 times 4 meters plus 10.33. And that is all equal to negative 5.66. And so that's this value right here, negative 5.66. And then we can see that negative 5.66 is the value of shear throughout this entire section. So shear doesn't change at all in this region. It just stays constant. Which makes sense because there's no loads being applied in this region, so there's no change in shear. Because remember, both shear and bending are directly dependent on the loads being applied to our beam. And then from 5 to 6, we have negative 3.67. So that would be about here. And let's label that here, negative 3.67. And so we can see that jump that I was talking about earlier. We have a jump here at x equals 5, which is why we don't include it in our domain, because it's a discontinuity. The shear, at that point, that's where shear is changing, so we can't really define it as one value. And then I like to just shade in the area under my graph so I can see clearly what it looks like. And there we go, that's our shear diagram. So immediately, without doing any further calculations, you can see, boom. Let me grab my other marker. We have max shear right there. Our maximum shear is 10.33 right at that support. And we didn't have to do any calculations for that. All we did was we simply plot our equations on here, and just by visualizing it, we were able to see that immediately. And that's why plotting these equations is such a powerful but also simple tool to find some of these critical points. So let's repeat the same thing for the moment. So for the moment, we know that we will start at 0. We can see that from this equation here, because at x equals 0, we just have nothing. But we also know we have a pin support right here, and pins cannot support a moment. So we know that we'll have to start at 0. It's just a good way to double check that this equation makes sense. And then we have a negative x squared term. So recall that when we have x squared, this represents a parabolic formula. X is linear, and a number is just a constant. So when we have a x squared that's negative, we have a parabolic shape that's curving downward. So we'll actually have something that looks like this. And don't worry about being exact when you draw it, just as long as you capture vaguely the shape that it should look like. So in this case, we know we should have a upside down parabolic shape. And then if we want to get this value right here, we can do what we did last time. Let's just use our formula. This formula. So that will give us, so we have negative 2x squared plus 10.33x. Let's sub in our value. This is x equals 4 meters. That's where we want that's what we want to know the value of. Plus 10.33 times 4. What does that give us? We go to the calculator. We get 9.32. This is 9.32. Okay. And then we move on to our next equation when we're between 4 and 5. So we see that it's a linear, because the highest x term is just to the power of 1. And we have a negative linear function. And it has a slope of negative 5.66. So I know it's going to look something like that. And then I'll check what that value is. So we have negative 5.66 times, x is equal to 5 at that point, so we'll go times 5 plus 32. And that is going to give us roughly 3.7. And remember that when we use x, we're always measuring from this leftmost point, which we have denoted as x equals 0. Okay. And then so we have our two values here. And then we see that we have another negative linear function with a slope of negative 3.67. And because I'm rounding, it's going to be a little bit off, but when we have a negative slope over a distance of 1 meter, we know that we're going to just simply subtract the value of that slope. And I don't think I explained that in the best way, but we can just double check our answer to make sure this is making sense. Let's check what this value is. So we'll plug in x equals 6, because that's where we are in our graph, into this equation. 3.67 times 6 plus 22. And that is going to be equal to 0. And it's not exactly 0 because this is actually 0.66666 and then a 7. I just rounded, so it's a little bit off, but we know that this is going to come down to 0 because at a roller, we know a roller does not support a moment. There is 0 moment acting at this point. And then I'll just go ahead and shade in our graph. And then, wow, look at that. We see we have our maximum moment at x equals 4. Just like that, we didn't have to do any calculations. We can just see directly from our plot where the max shear is and where the max moment is. And that's why these graphs are just super fast and super easy to use, because they can give us that information just like that. And so that is everything we need. It's worth just like looking over your plot and making sure it makes sense. We can see that our moment is entirely positive, which means that our beam is always bending in a curvature that's like in the shape of a smile, which makes sense because most of the load acting on our structure is pointing downward. And so we're kind of getting that, what this positive moment is showing us, because positive moment means smile. It's showing that our beam is bending like this, which makes sense because you push down on here, the beam is going to like lower down here and then curve up to the supports. But that's pretty much it. And that's how you use the method of sections to create these diagrams. Again, if you want to see the full method of sections, I would recommend checking out my video on deriving the shear and moment equations. Those two things are the exact same thing. When you're deriving these equations, you're applying the method of sections. And so that is pretty much it. I'll end with a quick summary and 3 steps just to remind you guys of how this goes. But when you want to plot shear and bending moment diagrams using the method of sections, the first step that you're going to want to do, derive shear and moment using method of sections. Okay, once you get those, the second step is make sure equations have proper signs. And so, remember, the way you check to make sure your equations have proper signs is look at the sign convention, look at the directions you used for shear and moment when you made your cut, and then see, do those agree with the sign convention I'm using here? In our case, our shear on the right was in the opposite direction as where it should be. On the right, we know that positive shear would have a force downward on that side. And then our moment agreed, so we didn't have to change that. But once you have those equations figured out, the last step is simply plot equations. And then label key points. And remember, to find those values, the values of those points, simply plug in x value into equation. And make sure that when you plug in an x value into your equation, make sure that you're using the proper equation that is designated to that span on the beam that you're looking at. So if we're between 0 and 4, we can use this equation. If we're between 4 and 5, this equation, 5 and 6, this equation, and so on. So that's pretty much it. I hope that everything made sense, but if you caught any errors or have any questions, please feel free to ask away. And as always, thank you for watching, and I'll see you guys next time.